Example 5, according to a study, 78.7% of those earning a teaching license were female. Suppose 5 people who earned a teaching license are randomly selected. A, find the probability distribution for the number that are female. The number that are female is our random variable. Okay, so we want to know how many are female, but the probability of each of those possibilities. It says 5 people are selected, so you could have anywhere from 0 to 5 females in that group. So this is going to be kind of a big probability distribution, I suppose. But that number, that random variable, could take on values 0, 1, 2, 3, 4, or 5. Now we need to talk about the probabilities of each of those random variable values. Okay, so we've got this value, this 78.7% here. 78% or 78.7% of those were female. So this is a binomial distribution, and you can tell because in a problem like this, it's either they are or they aren't. Okay, they are or they aren't. And so they either are a female or they aren't a female. So if we think about it, we want 0 females for the first entry in our probability distribution. And so the way that works is going to be out of the 5 selected, we're going to choose 0 of them to be females. And so this probability of 0.787 is going to happen 0 times. Okay, so then what does that leave? Well, that leaves the other 5 are not female. So if you think about the probability of not female, you'd have to do 100% minus 78.7%, which is 21.3%. And so this value would be 0.213 to the 5th, and that represents the number that are not female. Okay, so do we want to put that in the calculator? 5, choose 0. You should know that's 1 times 0.787 to the 0. You should know that that's going to equal 1 times 0.213 to the 5th power. It's a really, really low probability, 0.0004. Again, I like 4 decimals, so 0.0004. Okay. So now 1 female implies 4 non-females. So you've got 1 of these 0.787s and 4 of the 0.213s. Okay, so if I choose 1 and 0.787 to the 1st, let's close that off, times 0.213 to the 4th, 0.0081. Once you get started, it's pretty easy to complete this because it's just a pattern. And you recognize the pattern. The next one, if we want 2 females, that's 5, choose 2. That's 0.787 squared and 0.213 to the 3rd power. Notice the exponents have to add up to 5. That's the total number of people selected. So I'm not going to show you how to do that on a calculator, but you type that in on a calculator, you're going to get 0.0599. And then we're going to do the next one. 3 females, 2 non-females. Four females and 1 non-female. Five females and 0 non-females. Right there. Oops, not a 6, it's a 9. Now, those numbers should add up to 1. If they don't add up to 1, it's going to be really, really close, and that's just going to be, it's going to be off maybe because of rounding, because this isn't actually 0004, and this isn't actually 0081. It's rounded off. So if you're off from, if you're not equal to 1, it should be really, really close, and it's off just because of rounding. Part B says find the expected number of females. So we know how to do this. We know how to find this expected value. We're going to take 0 times this. Multiply and add, and we get approximately 3.935. That's the expected value, or the expected number of females out of 5 selected. We'd expect 3.935 females out of the 5. Okay, so let's go ahead and do this next one. Suppose a family has 3 children. Find the probability distribution for the number of girls in the family. Number of girls out of 3 children. So this is very similar to the last problem, isn't it? It's kind of the same thing. Selecting 3, so you could have up to 3 girls. So 3 choose 0. And in this case, we're kind of assuming that it's a 50-50 shot here of having a girl or having a boy. Okay, so 0.5 for girls, 0.5 for not girls, I guess. One girl and 2 not girls. 2 girls and 1 not girl. 3 and 0. So when we multiply that out, we get 0.125, 0.375, 0.375, and 0.125. Exactly. There's no rounding here. Histogram. I'm going to go 0.1, 0.2, 0.3, 0.4. That was 0.125. 0.375. And the same thing. And 0.125. Again, I think it makes a lot of sense to write that in if you can't tell what the values are. Like that. C says find the expected number of girls in the family. Well, we can just do the same thing that we've been doing, of course. And when you do that here, you get the answer of 1.5 when you multiply all that out. Okay, but as you recall, or maybe you don't recall, but if you go back here and look, the expected value has two different formulas. And we've done this one every time, but in a binomial experiment, you can also find the expected value with this simpler formula, n times p. So if you think about it, this is a binomial experiment, so either it is or it isn't. We could have instead said NP. So the number of trials in this experiment is 3, and the probability of any one of the trials, or probability of finding a girl, you'd have 3 times 0.5. 3 times 0.5 equals 1.5. Okay, so that was maybe a little bit faster. Let's see if that works in the other one. Okay, remember how the probability was 0.787? I wonder if we could have just said 5 times 0.787 and gotten the same thing. Let's see. 0.3935, 0.3935, same thing. Okay, so remember, this only works for binomial experiments, so you couldn't have used it in some of the other examples, especially not this one. That's not a binomial experiment. But if it's a binomial experiment, and if you recognize it's a binomial experiment, you've got this simpler equation for finding expected value. If you don't recognize it, though, you can always do the other way, the long way.